Have you ever tried to predict the path of a ball and realized that with just the smallest shove, it lands somewhere completely different? That idea, small causes, big outcomes, has a name in math: Lyapunov growth. Now here's the twist. Near a black hole, small differences aren't about your hand slipping on a couch. They're about tiny offsets in the angle of a photon. Imagine two light rays that start almost identical at the edge of a black hole's neighborhood. One whips into the hole, the other escapes to infinity. In the middle, there is a razor-thin region where the photons don't simply fall or flee, they loop around. And because those orbits are unstable, chaos isn't just possible, it's inevitable. The question isn't whether black holes can be chaotic, it's how does the geometry of space-time itself create exponential divergence, and why does that produce what astronomers actually see as the photon sphere glow? Before we get to the chaos, picture what black hole meant for most of physics. After Einstein, the prevailing intuition was deceptively simple. Gravity is a sink, and everything once inside is doomed. But the details of general relativity are stranger than the slogan. When light moves near a black hole, it doesn't follow Newton's gravity as a force picture. Instead, it follows the curved spacetime itself. Decades of work in the 1960s through the 1980s clarified that there can be special trajectories bound in the sense that photons can orbit. For the simplest case, an uncharged, non-rotating black hole described by the Schwarzschild metric, there exists a spherical shell of unstable circular photon orbits. This photon sphere sits at a fixed radius, not at the horizon itself. It's like an invisible racetrack hovering outside the event horizon, but the key is instability. Perturb those photons slightly and they don't settle back onto the orbit. They peel away, either plunging inward or escaping outward. So the stage is set. A geometric racetrack, instability, and light, meaning observable consequences, not just theoretical curiosities. Now the deep dive, photons in curved spacetime can be treated like particles moving in an effective potential. If you separate the equations of motion using symmetries, the radial motion of a photon can be expressed in terms of energy and angular momentum. The effective potential has a maximum at the photon sphere radius. A maximum is the mathematical opposite of a stable bowl. Imagine a marble balanced on the top of a hill. If it starts exactly at the peak, it can remain there, but any tiny nudge sends it rolling down one side or the other. That's the instability at the heart of photon sphere dynamics. For a Schwarzschild black hole, the critical radius corresponds to equals 3m, where m is the black hole's mass in geometric units. Photons with just the right impact parameter can orbit there. But just right is not an encouragement, it's a knife edge. Lyapunov growth describes how rapidly nearby trajectories separate in time. Suppose two photon rays have slightly different initial angular conditions, corresponding to slightly different impact parameters, because the orbit is perched atop an effective potential maximum. The radial coordinate behaves like an inverted harmonic oscillator near the peak. In that approximation, the deviation grows exponentially with time, delta tilde delta E to the peak, where lambda is the Lyapunov exponent. The exact value depends on the black hole's parameters, but the qualitative mechanism is universal. A local maximum of an effective potential creates exponential sensitivity. In practice, time can be thought of either as a fine parameter along the photon or as coordinate time measured by a distant observer. The key point is that the instability produces exponential divergence, not linear drift. This is where the photon sphere chaos becomes more than math. In the real universe, we don't track individual photons, we observe images, spectra, and timing. Yet the same unstable trajectories govern what happens to light attempting to skim around the black hole. Photons can execute multiple loops near the photon sphere before diverging. The number of loops depends logarithmically on how close their impact parameter is to the critical value. That leads to a cascade. Near critical photons orbit many times, while farther ones peel off sooner. When many photons take these near-critical paths, the black hole's shadow isn't just a dark disk. It includes a surrounding ring-like feature caused by light that performs multiple windings. The instability amplifies the effect of small differences, smearing trajectories into structured, predictable patterns. Chaos at the level of individual paths, order at the level of observable statistics. What about the story behind this? The classical result that an unstable photon sphere exists came from solving the geodesic equations in the Schwarzschild geometry. But the modern connection to Lyapunov exponents emerged as researchers asked a sharper question: can the instability rate of null geodesics be measured indirectly through quasi-normal modes in lensing? Quasi-normal modes describe how black holes ring down after perturbations, and remarkably, their damping and oscillation frequencies relate to the properties of unstable photon orbits. The same parameter that quantifies exponential separation also controls characteristic frequencies observed in gravitational wave signals from black hole mergers. So the chaos is not an abstract label. It's tied to quantities we can infer from data. These broader implications matter because they unify three worlds that often feel separate: dynamical systems, gravitational geometry, and astronomical observation. Lyapunov growth provides a concrete route to quantify how chaotic a black hole region is using the geometry of light's trajectories. This influences theoretical ideas about chaos, bounds, and information scrambling, concepts that connect black hole physics to fundamental questions about thermodynamics and quantum behavior. Even if you don't care about quantum information, the practical implication is clearer. The same unstable orbit that creates photon sphere rings and shadows also shapes how black holes respond to perturbations, affecting signals that modern detectors chase. In other words, chaos leaves fingerprints. The conclusion is simple but profound. We started with an open loop. Can a black hole turn tiny differences into dramatic outcomes? The answer is yes, because an unstable photon sphere acts like a hilltop for light. The effective potential peaks at a specific radius, and near that peak, deviations grow exponentially, captured by a Lyapunov exponent. That exponential divergence doesn't stay hidden inside equations. It organizes the messy paths of many photons into observable shadow and ring structure, and it echoes in the characteristic ringing of black holes. So when you look at images of black holes, dark shadows, bright rings, you're seeing not only gravity, but instability encoded in space-time itself. That's the mic drop. The universe doesn't just bend light around a black hole. It amplifies uncertainty until it becomes a signature. If you want more physics that connects deep math to real observations, subscribe.